So today I am planning to just go through a few what's it called? A few different circuits that I found on either either basic circuit analysis, from Wiley, and this one's from Pearson Microelectronic Circuits and Devices. Um, so yeah, let's just go and do that. Um, so let's start. I'll just clear this out. New blank circuit. And we will stop everything. And we are going to start with figure 1.33 on page 30 of Microelectronic Circuits and Devices. Doo-doo-doo. 1.33. This one here. Draw. We have a resistor, another resistor, another resistor. Then we'll just draw in a wire here. Oops. Delete. Just draw on the input source here. Actually, add voltage source. See which way it goes. Yeah, okay, so this way. Then we'll draw in the wire. There we go. Now we'll draw one more wire. There we go. Oh, let's do outputs and labels. Voltmeter. Okay. So I am just gonna describe what I think will happen here. All right. This actually isn't a voltage one here. This is a current source. Sorry. Puts in sources. Voltage source, ground. Do they not have a current source? Inputs and sources. Sorry, I had a text message come in. Yeah, I don't see anything. Okay. Let's just do this one with a voltage source then. Edit. $10K. It is. Okay. Actually, we can do the one on top, where those are all just 1Ks anyways. Okay. Click OK. So, this, I would think, this voltage source will, what do we have it set at? So we have it set at 5 volts. In 1.32, which we'll do now instead. Sorry, I'm just looking at the messages there in case somebody sends a message. But yeah, 1.32 we're gonna do instead. it had 12 volts, and then all of these were 1K, and then it had this as the output. So what my thought would be, what will happen is that we will have a certain amount of voltage being spent across here, and then the rest will be divided between these two. So this, since these two are in parallel, that means that they're going to show about 500 ohms in total. So that 2/3 of the voltage will get burnt across here. So then, since we're dealing with a 12 volt one, that would be 8 volts. So I would expect 4 volts to be across here and here. So this, I would think that the 4 volts would be here because this would be extremely high impedance. But this could also just not show anything. Yeah, well, let's see what happens. Yeah, so this shows basically nothing across, and then since these are the same, 6 volts is evenly split between them. I don't think that's what they were looking for us to do. So let's just remove that. And we'll imagine that's just an open circuit. And then we will draw just a wire here. So now, let's look. I'm guessing 4 volts will be spent across both of these. So yeah, 4 volts and 4 volts. Okay. Cross that one off. And go to 1.64. Yeah. So 1.64 on page 33. That's that top one. Oh, let's get another current source. We better skip it then. We're going to go to page 89 now. And we're going to do 2.27, which this gets into funner stuff anyways, I do believe. Yeah. Because now we get stuck into the... why did I pick that one? Oh, I think I meant 2.26. We can do both though. But we're going to get stuck into op amps now, which is much funner anyways. We're going to delete that off. And we'll draw active building blocks, op amp. Yeah, plus on top. We're just going to use the ideal op amps for this. Mostly, then I think it is... okay. I think that it will be just easier. Then we won't worry necessarily about the inconsistencies like that there would be an eye bias and such through here. We'll just assume that they are perfect. There's no current that goes into the input. These like the two inputs have the same voltage or want to be at the same voltage. All of that jazz. So now we will put in input source. voltage source. I'm going to put a 1-terminal voltage source in. Then draw, we'll add the resistors. It has one resistor there. Has a resistor here. And then it has another resistor here. And then it has its ground. Now we'll draw the wires. Right there. Right there. Right there. Then this one goes into that. There we go. I'll just stop it, because we will analyze it now. So, well, first I think I need to change modified. So we'll just use, it doesn't actually give us a non-inverted amplifier figure 2.5. Let's go to 2.5. Now we'll just put in our, we'll just keep these as they are here. So here we'll also draw in outputs and labels. Test point, we'll say. Okay, so there's our test point. So, as I said, this input here will obviously be at 5 volts. Now, over here, that means that this will also be at 5 volts. For that to be true, then we must have some voltage here. Now, to see 5 volts here, that means that 10 volt, yeah, so these are both the same. So that means that a total of 10 volts has to pass through here. Okay? Now, that also means for 10 volts to pass through here, that means that 5 volts goes through here, which means that, what would that be? 5 volts, 5 milliamps would be flowing down through here, and that would basically compensate and spread both of those across. So let's just see. Yeah, so we get 10 volts. Oh, we get 5 volts flowing this way. All right, so we have actually a reverse current happening here. I didn't think of that. But yeah, since this is 5 volts there, that's 10 volts there, that means the current would flow in the opposite way. Yeah, no, I never did think of it that way. Well, I did think of it that way, it just never occurred to me right now. So down here, we have 5 milliamps flowing in both. Now, let's stop this again. C, we'll change this to, say, 3K. Okay? So now, we have this as a 3 kilo ohm resistor. We have the 1 kilo ohm resistor. Now this test point and this is this test point's not correct necessarily now, but we still need to see 5 volts here. So to see the 5 volts there, again, we need to have some sort of amount of current going through here that causes us to have 5 volts over here. Now, believe what we would have end up seeing this case. Well, yeah, we have a range of minus 15 to 15 volts. So I'm gonna venture a guess here that we are gonna end up actually being maxed out at 15 volts, because if we had 15, yeah, because this should expand out 3 times as much as this in voltage. So we're gonna go set this up to try to get 20 volts, basically, so that we would have. Nope, no, I'm wrong. Yeah, I'm wrong. No, because we need 5 volts here, so that means 5 volts gets expended across here. Yeah, sorry, this is the better way to do it. So that means there would be 5 divided by 3 would be, frick, why did I make up this one? Let's change this to 5K. Then I don't have to do somewhat complicated math. So then we would have a milliamp going through, since this is 5K. If we have 5 volts, has to be here. So 5K, a milliamp. That means 1 volt gets expended across here. So this output will be 6 volts. And then we will just have a single milliamp coming out of here too. Let's see if I'm correct. And yep, we have 6 volts. We have about a milliamp. And about a milliamp. Okay, now let's stop. Should I do one more change on this one? Yeah, I think we can move on. So let's reset this, and I'll just cross off this one. Yeah, we might come back to that, but we're gonna go to 2.43 on page 92. Yeah, let's do it. Okay, so we delete that. We could keep those in. We will edit this. Nope, can't edit that. Okay, let's delete it then. We'll draw active building box, negative on top, and then I'll escape here. Right there. And there we go. Now we got that all connected, but this circuit actually has us grounded out the positive voltage here, and it has us put it in a capacitor here. Passive components, add capacitor. Doesn't say what capacitance. Escape. Just delete this here. Draw. I think I'll actually do a active components. No, I want inputs and sources. Add AC voltage source right there. And then, yeah, what to give us values for this one? So doesn't give us values that it wants it there. So I'll just keep the current ones that are in there, the 1K and 1K. And I'm going to just take a idea of what the output of this will be. Should know off the top of my head, but sometimes I don't. Because I just did this lab, but I'm trying to just analyze this all on the fly here, just for fun. But anyways, I think if you think of this again, this is going to be at 0. So that means that this input wants to be at 0, so that this op amp, it's going to do whatever it feels it can to, like the output is going to do whatever it can to make this 0 volts too. And we will, at some point with this AC source, have a voltage over here. Now, that voltage will also be compounded with, or like it will be affected by whatever this capacitor is doing. So let's just start actually with a, I could leave that in. Let's start with a square wave. And we're going to turn this down, edit. I'm going to put it to a half a hertz. Maybe it doesn't like half a hertz. I go apply. Okay, good. Okay. So now when this applies, I guess it's at 5 volts there. So say it's applying 5 volts. There's no charge on this capacitor at the time. So it's going to charge up. And as it charges up, this is going to see a voltage, a positive voltage. Now it'll take a while though to charge up. And then this, as it is getting charged, it's going to try applying a negative voltage to try and offset it. So let's see if that's what happens. Because it's like this output here is going to try and make this 0. So we're applying it to the inverted input. So whatever we apply to the inverted input, it's going to do the opposite. So we're applying a square wave, and then this will slowly ramp down, I guess, in the negative direction. So let's just run that. Yeah, so right here, seeing $5 volts. Let's make this a bit smaller. Say 100. So we reach some sort of an equilibrium there. Edit. Oh. Okay, let's just increase the 5. Okay. Minus 5 volts. So I'm going to watch the test point as I am holding there. Right now we are applying minus 5 volts. Now we're applying minus... Okay, I need to slow this down a little bit. Not being able to pay much attention again. We'll say 10. Apply. So we went too slow, now we were going too fast. So 5 volts. You can see it is what is it doing? It's like oscillating a little bit. Yeah. I'm gonna go view in new scope. I see what it's doing. It's tracking the charge time of it. Now, why would it be doing that? So I guess, yeah, because this will charge up to a certain voltage, but then this will be seen on the other side of it. So whatever voltage gets applied, if we apply 0 volts here, this will just charge up, say 5 volts there, and you'll see 0 volts at this point. Okay. I think I sort of understand what's happening here. Let's just increase the frequency again. Okay. Then we'll watch it in. Yeah, so it's just basically making a... Yeah. Interesting. I think... What is my next circuit I'm going to look at? If anybody has a circuit that they would like to look at, I'm taking suggestions as well. I'm at 2.43. Let's go to page 304 now. And do 5.99. There we go. So page 4. So now we are going to do... Yeah. Let's just clear this. We are now doing 3-terminal devices, and this is going to be a nice little BJT circuit. New blank circuit. Draw. Active components. Bipolar transistor. Right there. Nice little NPN. Now it's going to ask us for a current source again. But if you had been here earlier, you would know that it actually doesn't. This doesn't have current sources in it. So what we will do is we will just apply, I don't know, a voltage source and a resistor, which, guess what, makes a current. So there we go. So that would be 5 milliamps. We actually want, it says 40 microamps, but since we have plus 4 volts, what we will do is we won't apply 5 milliamps. We'll apply, let's say, wanted 20 microamps. We can apply, if we that 20, we'll apply 200K here, say, then that should be 25 microamps. Yeah, then we'll just draw a ground. What's the sources? Ground. Yep, 22.4 microamps it says. Because there is about 1 diode drop here, so about 0.6 volts of a diode drop. Next, we need R1. Or like a It's another resistor. They call it R1. We can call it whatever we want. Could call it 1K. Sure, there's a nice dinosaur from Land Before Time. I could call it 2. I always liked that show. Anyways, we'll apply 5 volts there. What did it want? It wants us to apply 15 volts here. Edit 15. Apply. Okay. Draw wire. And I'll just stop it for a second. So it wants us to find VCE of the BJT. I don't know if I'll do that. I might just talk about the circuit like I did before. So, as I said, they just said, oh, there's a current source. It's supplying 20 microamps to the base. I don't have that current source, so I went and I just said, well, I can apply 5 volts to the base through 200K resistor. And by doing that, we make about 25 microamps, I said. But it turned out to be 22.4 or something, the Falstad simulator said. Now, the reason why I would have calculated that is because, like I said here, there's a diode drop. It would be factoring in on this transistor. So that's why. What did it want this? Oh yeah, it wants this to be a 1.5. Okay. So let's put 0.5 there. Apply. Okay. Now we're going to apply this 15 volts here. Now, since there is enough current going through here, we can assume a beta of, say, 100. That means that there should be, so we have 22 microamps going through. A beta of 100 means that there should be 2.2 milliamps going through here, or up to 2.2 milliamps. This combination here would want 10 milliamps. So that means that since we say we have 2 milliamps, not 2.2 milliamps being drawn through here, 2 milliamps. If that was the case, 2 milliamps times 1.5K, that means we would have 3 volts across here. So then I would expect 12 volts here, I guess. Let's see. So 3.2 volts is being sort of burnt across this 1.5K. And then at VC, we see 11.7 volts. Then VE, obviously 0 volts. So I was pretty close to right, 12 volts there. That's interesting. I don't know. That's a bit of an odd circuit, but let's drop this. No, actually. Let's raise this up, okay? Let's put it to 30K. So 30K here. Okay. So now we have made it so that only 2 milliamps should be going through this resistor here. In like if it was just a regular Ohm's law circuit, 2 milliamps. So that would burn up everything. So then there'd be 0 volts at C. But I'm guessing there isn't. Let's check and see what it is there. First, we'll see there. So it's burning up all but 0.9 volts basically, or 0.09 volts. Yeah, it only has like 90 millivolts. So it is effectively like, oh, it's only drawn half a milliamp. Yeah. So this, yeah, no, that makes sense. I think I did overdo it a bit. Let's edit this. We'll put the 7.5K here. Okay. So now we'll see some voltage at the other place. Not much. But yeah, see, we eventually just hit a limit. Let's go back to our 1K. Sorry, I'm spending a bit of time on this circuit. I want to demonstrate one more thing. So if I can actually do this. I lower this. So now I've made it so that about 40 microamps goes through here. So that means we'd have a max of about 4 milliamps going through here. Yeah, see, we have 4.366. There it said, yeah, 43.66. So now 4 milliamps, that means we would expect about 4 volts going across here. And yeah, we have that. I don't know, I think we've probably spent enough time on this circuit. I think I will move on. Cross that one out. And we just have, oh, we don't even have this. Did I mark that circuit there? 516, 116? I didn't. But, you know, I think we might do it anyways. It's a Darlington pair version of it. So I'm just going to stop this. And we are going to draw in another nice little bipolar junction transistor. Active components. We could draw in there, but we'll just wire one up ourselves, I think. So now I'll just escape and move that there. Move this over here. Then let's go here. There. There. Now go there. Now you go over there. I think that's it. So now this will effectively yeah, did I do that right? Well, what if I did it right? What should happen now is that the current through here will get increased another 100 times. Let's see. Yeah, so it looks like I did that right. Well, what, not 100 times, because of course this actually wouldn't go that high. Basically, it is only 15 volts across a 1K, so that means it would have about a max at 15 milliamps, and we have 14 milliamps going there. So that means we must be using up some voltage. Yeah, right there. Let's see if we can coax it to go down more. But no, we can't really. See, watch if we go like this. We'll eventually see a slow in. Might take a while. Oh yeah, it's gonna take quite a bit. So, I guess we could figure it out. Let's do it. 10, yeah, there we go. Now we're at 10 mega ohms, and we finally see quite a decrease. Now we only have 4 milliamps. Okay. That was one I just saw. I think this was, yeah, this was the one that I was planning to do next. Had a voltage source, 10 volts and minus 10 volts, and a PNP transistor. Oops. We will just go new blank circuit. And draw inputs, not inputs and sources, active components, PNP, there. Then we want a 10K resistor and a 5K resistor. We'll put in the values after here. Then it ties a voltage source directly in to the base of the transistor. I have a feeling that the circuit might be upset with that, but we shall see, I guess. I'm just going to click the stop here so that I don't get, I can't cheat, basically. Because I like to not rely solely on the simulator, obviously, and to figure things out myself if I can. It's just much more rewarding that way, I find. I'm doing it in this format because, like, normally, well, not normally, I shouldn't say I do it all the time, but it's nice if I can do it on the bench and build these circuits. But I'd like to do that more, but a lot of the times I'm trying to complete the labs I have assigned, and yeah. Anyways, I think, what did they want that to be? Consider PNP over what range of VB, relative measure to ground, will Q1 operate in the constant current region? Okay. So, I don't know how to answer this question. This I guess this voltage always has to be higher than the one seen here, or else it will not work, I think. That's what they're getting at. In that case, then it shouldn't. Let's just run it. I don't have a prediction here. So we have I'm gonna have to think about that one a bit more, because I don't get what precisely they are asking here, or what this circuit would be used for. If anybody has any ideas, maybe they could feel free to comment. But I think I will just star that one and move on, instead of me just sort of mumbling to myself for another, I don't know, 15 minutes or so. So we will go to page 504. I'm going to page 504. Ah, yes. This is one I wanted to do because I just constructed a circuit. I don't know. If you go to my my channel, you'll see that I have a new circuit that I've made to complete the part 2 of learning the art of electronics. Now these are different textbooks I'm getting these problems from just for fun, but there's I'm going through the textbook learning the art of electronics, as well as going through art of electronics while I'm doing that. And I made a little sort of dusk to dawn circuit out of transistors that requires a differential amplifier. Well, here I'll make up this circuit here. Maybe we'll construct that whole circuit later, since the stream, I'll be ending the stream in about 15 minutes. But anyways, yeah, so that's right. Then we put in a resistor here. Then, actually, yeah, we better just move that. We'll escape, move this up. This, maybe we'll move both of these down to get us some more room. Oh, oops. Right there. Yeah, let's draw a couple wires here. Draw one there to there, because we are gonna tie this into both of these bases for something I hope will make sense soon. We'll just ground the emitters here. It doesn't have them grounded, but I think I'll just ground them. Then I'll add a resistor here. And then we will just draw them together. Oops. Don't want a resistor there. We want just a wire. So now we'll draw in that wire. And we'll draw a, where is it? Inputs and sources there. Oh, I want to stop this first. Again, like just so that I don't give anything away. I want to give myself at least a moment to try and explain it in my own words before I just let the what's it called? The simulator do it for me. So here we better edit. Cancel. We will put this at. Yeah, cancel. So we'll just say 68. Okay, there. So what is going to happen here is that we're applying 5 volts, so we're applying the same voltage across both of these. When we do that, a certain amount of current, actually I'm going to make this better for easier math here. Say 50K, apply, okay. So 50K, that means that 5 divided by 50 is 0.1, so about 100 microamps. It's going to flow through here and into these bases, or part of it will flow into the bases. What it's going to do, for our purposes, is that actually only 100 microamps will flow through here. Yeah. So let's just see if I am right in saying that or if I am wrong. And it's saying 87 microamps. That's 89 microamps. So about, this is 87 here. Actually, the best way, how about let's do that? Just then you can see it even better. I'm going to draw in an ammeter. Outputs and labels. Add ammeter. Right there. Escape. Delete. Draw. Puts and labels. Add ammeter. There. So you see they are matched. Now if I edit this and put it down to say 25, now they'll be matched again. This all goes back again the way. Yeah, I wish you streamed before your AP Physics circuits test. Yeah. Well, there's always time to learn more. I just learned this. I'm learning this for fun right now. I was actually an applied physics major in university, but anyways, I'll get back to this. So, how I think of it again is I always I try to think of currents when dealing with transistors, because they sort of activate everything in this case. Like the beta, it's like it multiplies it and all that, just all based on current. So the way I think of it is that when you apply a voltage here, that current comes down here, and then that current, when you tie it into these bases, that means that the same amount of current will be flown into each of these bases, and then that will effectively make them both draw the same amount of current through them. Now, I'll maybe just to finish this off, I'm going to pull up my, like you see, you can input file, cancel, open file. I'm gonna pull up, is it in that one? Yeah, there it is. So this is the circuit I had made. It's my dusk to dawn light, as I call it. Now I just made a new video about it, and while making that video, I actually, for the longest time, I was having trouble figuring out why this circuit works. Okay? Until, so it occurred to me just after, just today, earlier when I was making that circuit, or making that video. So how the circuit works is that over here, you have this biased so that it sees 1.5 volts at this point. And there would basically be a certain amount of current going through here, asking for that amount of current, and triggering this to deliver that much. Over here, you have the same thing happening. But over this part, which is important, you see we have what the circuit we just made, a little current mirror, with this set to apply, to set that amount of current. Now, in that, we have that there. So that means that it's 41 microamps, roughly, has to go through this side of the circuit as well. Now, when this is a mimicking in the light, this photoresistor is very has a very small resistance, and therefore it's basically it's hogging all the current. It's applying most of it there. Now, what will happen if I say, now let's raise this up? Oops. I'm going to raise this up here to above 30K. Apply. Okay. So let's see what happens. Over here, we're seeing that the more current is going through this LED. But why is that? Well, let's go look at this part of the circuit here, these two PNP transistors. Now, you see here, we have another sort of current meter. Now, this one, though, is largely driven by how much current gets drawn in through this side of the circuit by this transistor here. Now, when we increase that voltage, and now there's only just under 1.5 volts being applied there, that means that this is pulling less current through it than what this one wants to pull through it. What that effectively does, because this one here, for this, it will be applying the same amount of current, but when we decrease this, or like decrease the voltage applied here, decreasing the current being pulled out of these bases, which decreases the current coming this way, well then we start asking for current from here to match the current that's coming from here. And then that turns on this LED over here. Now, one of the other things I realized is it goes both ways, right? So now, if say I edited this to be 50K, go apply, okay. Well, now that LED will turn off because now there's going to be a very little amount of current being called from over here, and then the extra current, see, this still meets up what it wants there, but the extra current will be actually called for through here and out. I don't know if that made too much sense. Actually, I should have made this video a little bit earlier and tried to do that, because I think I had a better grasp of it earlier today. Anyways, how about let's do actually a couple more circuits here. Just I want to sort of still flex my brain out a little bit. So I'm going to go to page 164 in the other textbook that I hadn't opened yet. And we're going to go back and do some more bipolar junction current. We're going to go back to op amps. So 4.9, I figured. Okay. Let's go new blank circuit. And draw we want to go active building blocks, ideal, up, ideal, minus on top. We're going to stop this again. This is a nice, easy circuit to analyze, I think, so I think I'll get it right. then my confidence will be back up. And there we go. Sorry, my phone buzzed again. But yeah, if anybody has any questions, I know Holster is disappointed that I wasn't doing this last week, so he could ask some questions for his AP Physics. But if anybody did have any questions, any sort of circuits that they would be interested in seeing, please tell me, and I'll try to get one in. Yeah, inputs and sources. Do a voltage source T terminal. Then, yeah, we will draw the wire there, over there, over there. Set it, so that's going to be 5 volts. So, again, from our understanding of op amps, we know that the voltage between these two wants to be the same. So right now, we're applying 5 volts to the positive input of the op amp. That means the negative input also wants to be 5 volts. And it will change the output to try and get us there. So the way it will change that output, in this case, oh wait, I wanted this to be 20K. Apply. Since it's applying it to the non-inverting input, that means it will try to raise this voltage up. Now, since we have 20K there, that means that when it tries to apply 5 volts here, and it's 0 volt, there are zeros down over here, then that means we're going to be putting about 5 milliamps through here. So it's going to be whatever voltage that would have 5 milliamps going through this 20K. So that would be 5 times 20. That would be 100 volts. So we are going to see 15 volts here, if I'm right, because basically this op amp will only go from minus 15 plus 15. So let's run. And yeah, we see 15 volts. Let's stop this. If we change this now to, say, something reasonable, let's go 0.1 volts. Apply. Okay. Now we go 20 times 0.1. We should be seeing 2 volts here. Let's see. It says 2.1 volts. So 100 millivolts. 1 second. Wonder. Yes, we see almost 100 millivolts. Yeah. Yeah, no, sorry. That is right, because it, whatever, right? Yeah, so we have to apply the full thing there. That's why. So this is, it's whatever we put at this positive non-inverted input will be multiplied by 21 in this case. Yeah, let me see if I should do, I'll go do this last circuit for 0.11. Okay. Then I think I will call it off. Thank you for everybody for coming out here. So it wants us to do another voltage source. Oop, wrong way. I think it wants us, yeah, it wants it to be applied here. I'll actually draw a new op amp as well. Because it wants the plus on top this time. That's how it drew it, so it's always easier just to follow what it drew, I find. Now it also wants 2 resistors. One there, and it wants another one here. We're going to sample from there. Add the wire. Go this down there, that, there we go. That one. Now we'll put another wire in right there. Oops. Okay, let's stop it right now. Right there. And then right there. Okay. So now this circuit, let's just think of our knowledge again. Oh wait. It varies. So we'll start with this being well, it says the 4K, and we're gonna start with the other one being 1K. Okay. So we're applying 5 volts again. That means this input wants to be at 5 volts. This is at 0. So this is almost, it's almost the same that we just dealt with. Let's just think it through though. So if this is at 5 volts, then this guy wants to be at 5 volts, so we should have 5 volts here. It means 5 milliamps going through here. That means we have to be applying something that would cause 5 milliamps to flow through both of these. So that's 5K resistance. And then we want 5 milliamps going through it. So 5 times 5 is 25 volts. We won't see that. Be 15. But yeah, this is basically identical to the one we just made. So we'll change this to 1. And now we should see 5. I didn't actually realize that when I created it, but yeah, it's definitely just basically the same. I think that I will shut it off now. Really, thank you to you 3 who were watching. Please, if you want, if you have any suggestions, please comment. I'm not sure how much of a delay from the time you see me till now is, but I'm gonna shut it off. I'll wait a little bit and see. So that's all the problems I picked out, except for a few that I decided to say that I might come back to them. Yeah. Well, yeah, I think I will stop then. Thanks to everybody for tuning in, and I might actually start doing these once every Friday. I know this is a Sunday, but I just came up with the idea. But tune in maybe Friday at 8 o'clock, like this time, and you might just see me again. Thank you, and take care.